Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared this video on how trays work and what is flooding. This will help you to understand basics of distillation. Tray types. Distillation towers are the heart of a process plant, and the working component of a distillation column is the tray. A tray consists of the following components: overflow or outlet weir, downcomer, tray deck. There are two types of tray decks: perforated trays and bubble cap trays. In this video, we will describe only perforated trays, examples of which are valves or flutter caps, V-grid or extruded valve caps, sieve decks, jet trays. Possibly 90% of the trays seen in the plant are of these types. Perforated tray decks all have one feature in common: they depend on the flow of vapor through the tray deck perforations to prevent liquid from leaking through the tray deck. As we will see later, if liquid bypasses the outlet weir and leaks through the tray deck onto the tray below, tray separation efficiency will suffer. Tray efficiency. Distillation trays in a fractionator operate between 10 and 90% efficiency. It is the process person's job to make trays operate as close to 90% efficiency as possible. Calculating tray efficiency is sometimes simple. Compare the vapor temperature leaving a tray to the liquid temperature leaving the trays. For example, the efficiency of the tray shown in this picture is 100%. The efficiency of the tray in this picture is 0%. How about the 10 trays shown in this picture? Calculate their average efficiency and you will get the answer 10%. As the vapor temperature rising from the top tray equals the liquid temperature draining from the bottom tray, the 10 trays are behaving as a single perfect tray with 100% efficiency. But as there are 10 trays, each tray, on average, acts like 1/10 of a perfect tray. Poor tray efficiency is caused by one of two factors: flooding, dumping. In this video, we will discuss problems that contribute to tray deck flooding. Downcomer backup. Liquid flows across a tray deck toward the outlet weir. The liquid overflows the weir and drains through the downcomer to the tray below. Vapor bubbles up through the sieve holes, or valve caps, on the tray deck, where the vapor comes into intimate contact with the liquid. More precisely, the fluid on the tray is a froth or foam, that is, a mixture of vapor and liquid. In this sense, the function of a tray is to mix the vapor and liquid together to form a foam. This foam should separate back into a vapor and a liquid in the downcomer. If the foam cannot drain quickly from a downcomer onto the tray below, then the foamy liquid or froth will back up onto the tray above. This is called flooding. Downcomer clearance. Check this picture. Note that the downcomer B is flooding. The cause is loss of the downcomer seal. The height of the outlet weir is below the bottom edge of the downcomer from the tray above. This permits vapor to flow up downcomer B. The upflowing vapor displaces the downflowing liquid. That is, the vapor pushes the liquid up onto the tray above, which is a cause of flooding. On the other hand, this picture shows what happens if the bottom edge of the downcomer is too close to the tray below. The high pressure drop needed for the liquid to escape from downcomer B onto tray deck 1 causes the liquid level in downcomer B to back up onto tray deck 2. Tray 2 then floods. Once tray 2 floods, downcomer C shown in this picture will also back up and flood. This process will continue until all the tray decks and downcomers above downcomer B are flooded. On the other hand, all trays in a tower below downcomer B will lose liquid levels and dry out when flooding starts in downcomer B. Now the following rules apply. When flooding starts on a tray, all the trays above that point will also flood, but trays below that point will go dry. An early indication of flooding in a distillation column is loss of liquid level in the bottom of the column. If the downcomer clearance, which means the distance between the bottom edge of the downcomer and the tray below, is too great, the downcomer becomes unsealed. Vapor flows up the downcomer, and the trays above flood. If the downcomer clearance is too small, then liquid backs up in the downcomer, and the trays above flood. To calculate the height of liquid in the downcomer, due to liquid flowing through the downcomer clearance, use formula delta H equals 0.6 multiplied by V square, where delta H equals 2 inches of clear liquid backup in the downcomer, due to head loss under the downcomer, and V equals to horizontal component of liquid velocity in feet per second, as the liquid escapes from the downcomer. To guarantee a proper downcomer seal, the bottom edge of a downcomer should be about 0.5 inch below the top edge of the outlet weir. This dimension should be carefully checked by process personnel when a tower is opened for inspection. It is quite easy for sloppy tray installation to distort this critical factor. Height of liquid on tray deck. As the liquid level on a tray increases, the height of liquid in the downcomer feeding this tray will increase by the same amount. Again, excessive downcomer liquid or froth levels result in flooding and loss of tray efficiency. The liquid level on a tray is a function of two factors: weir height, crest height. The weir height on many trays is adjustable. We usually adjust the weir height to between 2 and 3 inches. This produces a reasonable depth of liquid on the tray to promote good vapor-liquid contact. The crest height is similar to the height of water overflowing a dam. It is calculated from by gallons of liquid leaving the tray divided by weir length in inches power 0.67 and multiplying it with 0.4. The sum of the crest height plus the weir height equals the depth of liquid on the tray deck. One might now ask, is not the liquid level on the inlet side of the tray higher than the liquid level near the outlet weir? While the answer is yes, water does flow downhill, we designed the tray to make this factor small enough to neglect. Vapor flow pressure drop. We have yet to discuss the most important factor in determining the height of liquid in the downcomer. This is the pressure drop of the vapor flowing through the tray deck. Typically, 50% of the level in the downcomer is due to the flow of vapor through the trays. When vapor flows through a tray deck, the vapor velocity increases as the vapor flows through the small openings provided by the valve caps or sieve holes. The energy to increase the vapor velocity comes from the pressure of the flowing vapor. A common example of this is the pressure drop we measure across an orifice plate. If we have a pipeline velocity of 2 feet per second and an orifice plate hole velocity of 40 feet per second, then the energy needed to accelerate the vapor as it flows through the orifice plate comes from the pressure drop of the vapor itself. Let us assume that vapor flowing through a tray deck undergoes a pressure drop of 1 psi. Picture shows that the pressure below tray deck 2 is 10 psig and the pressure above tray deck 2 is 9 psig. How can the liquid in downcomer be flow from an area of low pressure, 9 psig, to an area of high pressure, 10 psig? The answer is gravity, or liquid head pressure. The height of water needed to exert a liquid head pressure of 1 psi is equal to 28 inches of water. If we were working with gasoline, which has a specific gravity of 0.70, then the height of gasoline needed to exert a liquid head pressure of 1 psi would be 28 inches divided by 0.70 is equal to 40 inches of clear liquid. Total height of liquid in the downcomer. To summarize, the total height of clear liquid in the downcomer is the sum of 4 factors. Liquid escape velocity from the downcomer onto the tray below. Weir height. Crest height of liquid overflowing the outlet weir. The pressure drops of the vapor flowing through the tray above the downcomer. We will discuss how to calculate this pressure drop in an upcoming video. Unfortunately, we do not have clear liquid either in the downcomer, on the tray itself, or overflowing the weir. We actually have a froth or foam called aerated liquid. While the effect of this aeration on the specific gravity of the liquid is largely unknown and is a function of many complex factors like surface tension, dirt, tray design, etc., an aeration factor of 50% is often used for many hydrocarbon services. This means that if we calculated a clear liquid level of 12 inches in our Downcomer, then we would actually have a foam level in the Downcomer of 12 inches divided by 0.50 is equal to 24 inches of foam. If the height of the Downcomer plus the height of the weir were 24 inches, then a Downcomer foam height of 24 inches would correspond to Downcomer flooding. This is sometimes called liquid flood. This discussion assumes that the cross-sectional area of the Downcomer is adequate for reasonable vapor-liquid separation. If the Downcomer loading gallons per minute per square feet of Downcomer top area is less than 150, this assumption is okay, at least for most clean services. For dirty, foamy services, a Downcomer loading of 100 gallons per feet square would be safer. Jet flood. This is a realistic picture of what we would see if our towers were made of glass. In addition to the Downcomers and tray decks containing froth or foam, there is a quantity of spray, or entrained liquid, lifted above the froth level on the tray deck. The force that generates this entrainment is the flow of vapor through the tower. The spray height of this entrained liquid is a function of two factors: the foam height on the tray, the vapor velocity through the tray. High vapor velocities, combined with high foam levels, will cause the spray height to hit the underside of the tray above. This causes mixing of the liquid from a lower tray with the liquid on the upper tray. This back mixing of liquid reduces the separation, or tray efficiency, of a distillation tower. When the vapor flow through a tray increases, the height of froth in the Downcomer draining the tray will also increase. This does not affect the foam height on the tray deck until the Downcomer fills with foam. Then a further increase in vapor flow causes a noticeable increase in the foam height of the tray deck, which then increases the spray height. When the spray height from the tray below hits the tray above, this is called the incipient flood point, or the initiation of jet flooding. Note, though, that jet flood may be caused by excessive Downcomer backup. It is simple to see in a glass column separating colored water from clear methanol how tray separation efficiency is reduced as soon as the spray height equals the tray spacing. And while this observation of the onset of incipient flood is straightforward in a transparent tower, how do we observe the incipient flooding point in a commercial distillation tower? The reason I can say with confidence on this subject is that I worked with a 4-inch demonstration transparent column at a refinery. I used the little distillation tower to explain to plant technicians how distillation towers worked. The tower's feed was windshield wiper fluid with blue dye. The alcohol went overhead, and the blue water was the bottom's product. Incipient flood. This picture illustrates the operation of a simple propane-butane splitter. The tower controls are such that both the pressure and bottom's temperature are held constant. This means that the percent of propane in the butane bottom's product is held constant. If the operator increases the top reflux flow, here is what will happen. 1. The tower top temperature drops. 2. The amount of butane in the overhead propane product drops. 3. The tower bottom temperature starts to fall. 4. The reboiler duty increases to restore the tower bottom temperature to its set point. 5. The weight flow of vapor and the vapor velocity through the tray increase. 6. The spray height, or entrainment, between the trays increases. 7. When the spray height from the lower trays impacts the upper trays, the heavier, butane-rich liquid contaminates the lighter liquid on the upper trays with heavier butane. 8. Further increases in the reflux rate then act to increase, rather than decrease, the butane content of the overhead propane product. This picture illustrates this point. Point A is called the incipient flood point, that point in the tower's operation at which either an increase or a decrease in the reflux rate results in a loss of separation efficiency. You might call this the optimum reflux rate. That would be an alternate description of the incipient flood point. bypassing steam trap stops flooding. Take an example. We have a distillation tower that floods. Delta P on trays below feed point is stable. Delta P above feed trays 16 to 22, increase from 1.3 to 2.7 psi. Condenser and reflux drum is internal in tower, and we cannot measure the reflux rate. The operator bypassed steam trap on reboiler outlet and flooding stopped. The panel operator concludes that flooding tower is due to defective steam trap. What's your opinion? Note that tower fractionation also improved after trap bypassed. The panel operator is quite wrong. When he bypassed the steam trap, he blew the condensate seal on the reboiler outlet. This permitted uncondensed steam to blow through the reboiler, thus reducing the reboiler duty. The reduction in the reboiler duty reduced the vapor flow up the tower and hence the internal reflux rate. This unloaded the trays and stopped the flooding. Panel operator's observation that the tower fractionation improved as a consequence of bypassing the steam trap was a positive indication that he had degraded tray efficiency due to entrainment. That is, he was operating above the tower's incipient flood point. Certainly, there is nothing amiss with his reboiler steam trap. He should try to water wash the trays above the feed point onstream, as the trays in this service are typically subject to ammonium chloride sublimation. Tower pressure drop and flooding. It is a characteristic of process equipment that the best operation is reached at neither a very high nor a very low loading. The intermediate equipment load that results in the most efficient operation is called the best efficiency point. For distillation trays, the incipient flood point corresponds to the best efficiency point. We have correlated this best efficiency point for valve and sieve trays as compared to the measured pressure drops in many distillation towers. We have derived this formula, where product of pressure drop across a tray section in 28 is divided by the product of the number of trays, tray spacing in inches and specific gravity of clear liquid, at flowing temperatures give us the value of K. Based on hundreds of field measurements, we have observed that if K equals 0.18 to 0.25, tray operation is close to its best efficiency point. If K equals 0.35 to 0.40, tray is suffering from entrainment. Increase in reflux rate noticeably reduces tray efficiency. If K greater than or equal to 0.5, tray is in fully developed flood. Opening a vent on the overhead vapor line will blow out liquid with the vapor. If K equals 0.10 to 0.12, tray deck is suffering from low tray efficiency due to tray deck leaking. If K equals 0.00, the liquid level on the tray is 0, and quite likely the trays are lying on the bottom of the column. And if K equals 1.00, tower is completely full of liquid. Carbon steel trays. One of the most frequent causes of flooding is the use of carbon steel trays. Especially when the valve caps are also carbon steel, the valves have a tendency to stick in a partially closed position. This raises the pressure drop of the vapor flowing through the valves, which, in turn, pushes up the liquid level in the downcomer, draining the tray. The liquid can then back up onto the tray deck and promote jet flood due to entrainment. Of course, any factor like dirt, polymers, gums, salts that causes a reduction in the open area of the tray deck will also promote jet flooding. Indeed, most trays flood below their calculated flood point because of these sorts of problems. Trays, like people, rarely perform quite up to expectations. The use of movable valve caps in any service where deposits can accumulate on the tray decks will cause the caps to stick to the tray deck. It's best to avoid this potential problem. Use of grid trays with fixed cap assemblies is preferred for most services. Optimizing feed tray location. From the design perspective, the optimum feed tray, for a feed with only two components, is that tray where the ratio of the two components matches the ratio in the feed. If the feed is at its bubble point temperature, then the feed temperature and the tray temperature will be the same, at the same pressure. But that's only for a binary feed composition. In multi-component distillation, the ratio of the key components in the feed will typically not coincide with the ratio of the key components in the liquid on the tray, even though the tray temperature is the same as the feed at its bubble point temperature. So, the question is, which of the following two criteria should be used to determine the feed tray location? Where the ratio of the key components in the liquid on a tray matches the ratio of the key components in the feed? Or where the feed temperature matches the temperature of the tray? You should practice it to identify both possible locations and then locate the feed nozzle halfway between the two options. I would provide two alternate feed nozzles at each of the other above locations, except the operators would likely never use them. When I refer to key components, I mean, for example, debutanizer, normal butane and isobutane. Depropanizer, propane and isobutane. Deethanizer, ethane and propylene. Gasoline splitter, isohexane and cyclohexane. All these services have feeds with dozens of other non-key components. Catacarb CO2 absorber flooding. A process engineer was hired to expand the capacity of the hydrogen plant that was limiting refinery capacity. The bottleneck was the absorber that removed CO2 with catacarb solution from the hydrogen product. This absorber was subject to flooding as the catacarb circulation rate increased in proportion to H2 production. That is, the solution was carried overhead with the hydrogen product. The engineer studied the design of the tower but could not see an explanation for the flooding. Nevertheless, he decided to modify all the 40 trays in the absorber. The materials were ordered, and the labor force organized. However, the morning the absorber was opened, he received a call from his assistant. He informed the engineer that, "There's kind of a plate in front of the solution inlet nozzle which is not shown in drawings and what you want to do with that plate." The engineer reached there and looked at the plate. Dimension X was only about 3/4 inch. Evidently, the plate was intended as an inlet solution distributor. He calculated that the delta P, as the solution flowed underneath the plate, was about 15 inches. Delta H inches was equals 0.6 V square, where V was the solution velocity through the 3/4 inch gap in feet per second. The plate was 12 inches high. As the solution rate increased, the liquid would back up over the top edge of the plate and be blown out of the top of the absorber. The engineer told his assistant to have the bottom 2 inches of the plate cut off to increase X to 2 3/4 inches and close the tower. When the tower started up a week later, the hydrogen plant bottleneck was gone. And you can understand the engineering contractor would have cost $3 million, but process and equipment knowledge has saved all this money. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos. Good day and good luck.